Okay, this is actually going to be the second video of optimization I wanted to show you in this video. If you go to my Edline site and click on that, these are actually all the links to everything that we did, and actually there's some extra stuff where it says if time allows. Nobody had time to do that, so don't really worry about that. But in the other video I showed you about the box problem. Here's the direct link to that if you didn't want to type it in, although typing this link in is very easy. These links are not so easy. Okay, so we're going to go through actually both of these. I already have them up here though. If you don't have your calculator out, you need to get this out so that we can do this problem. And so when we're looking at this type of website right here, all right, it says we have the cost to lay the wire under the water is $2 a meter, and cost to lay wire on land is $1 a meter. And I can change these if I want, but I'm going to just keep them where they are for now. And so all of this up here is water. The island, you know, is surrounded by water. That's what an island is. Then all this down here that's kind of like a pinkish color is land. And so look what happens when I move this slider. The cost is going to change because the links of the water versus the land is going to change. And so, you know, if I say, okay, water's more expensive, so I'm just going to move the slider all the way to the left, I actually, though, have covered, I have more wire than I need to. So that's not really the most cost efficient, because here we're trying to minimize cost, right? This is a business thing. Now, if I say, I'll just go straight to the power station, okay, well, that's minimizing the wire, but is it minimizing the cost? Not really, because the underwater wire is more expensive, so you're using all the more expensive. So surely there's some way. If you play around, if you go to this website and play around with the applet, you can change where the island is and the power station and all that. I'm going to be more focused about everything stays the same except this, okay? And if you notice, there's somewhere in here where it's like 16,000 something, whereas it jumps to 17 here and over here. So it's somewhere between 2 and 3. I would say like closer to 2 than 3. All right, so that's going to be my best guess right now. Okay, also just want to go ahead and give you a hint. This is in meters. These are in kilometers. Now you had to kind of read the problem to know that. All right, so when we go to do this problem with calculus, we're going to have to really keep that in mind. And so if we look down here at these, we've already used the sliders. I'm not going to do the other. You can do that on your own time if you want to change the cost, blah, 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 okay? But we have done two. Move the blue point on the shore to see what the total cost of the project changes. We found the minimized cost. It's 16,000 something. All right, under what circumstances will the minimum cost be achieved? All right, now I kind of talked about 3, so I'm just going to skip to 4. Okay, so we're just going to skip to how would you do this without the applet, in other words. And so it says if you have messed this up, where it's all sorts of different stuff, you can always hit reset up there at the top right, and then changing this blue dot is fine. We'll put it back here where we think our experimental, using the computer applet, what the minimal cost is. All right, and so I'm going to go to my notes over here, and I'm going to see that there is there's a picture. And let's go ahead and label this picture. Now, I'm going to go ahead and tell you X should be the base of this triangle. Now, X is not representing the wire under the water or the wire on the land, okay? And so I'm going to go ahead and write that, though, while we're already talking about it. This is the water, this is the land wire. X is something totally different, but X does tell me how far, you know, from the island, perpendicular basically, how far down the land should we connect the wire from the island. Or, you know, power station, where should we lead off? And we could get into angles and all that, but we're not going to in this problem. So X is always going to be this right here, because I have to come up with an expression for the water and an expression for the land. Okay, I want you to go ahead and write this as 4,000 meters, even though it's 4 kilometers. And this whole thing is going to be, it's 10 kilometers, so it's going to be 10,000 meters. All right, let's think about this. Right triangle. We know we got Pythagorean theorem. So the right triangle, if we think about the water, we should be able to do 4,000 squared plus x squared, and that equals the hypotenuse squared. So if I just put a big square root over it, I'm good. Do not simplify this. This doesn't even simplify anyway. If you try to simplify it, you're doing bad math. I'm not going to get into it in this video. Leave it like this. Okay, for the land. This one's a little bit easier to see. We have 10,000 for the total base of this picture, and X is this piece over here. So if we knew what X was, we could subtract it from 10,000. So let's just do that. 10,000 minus X. And so this was kind of like in the box problem where we got our length and our width in terms of X. That's what we had to do here, okay? Now, when they did this in class, I kind of gave them some hint cards. And so, but I don't have that on here anyway. But I'm going to be your hint. All right, so that's that part. I'm just going to continue to work up here so I don't have to keep sliding down. All right, so let's think about what the cost would be. It would be however much the wire costs underwater times the meters of that wire plus, okay, it would be whatever the land meters are times the land cost, all right? In other words, it would be $2 a meter times the total number of meters. Again, do not simplify. We're going to use our calculator anyway. If you try to, the more stuff you try to do by hand on this, the worse it's going to be. All right, that's the cost of all the underwater wire. Now we're going to add it to 1. You really don't need the 1, but I wrote it just to make sure you see where it went. Times 10,000 minus X. Okay, so this is my cost in terms of X. So I could have written this as C of X. Okay, that's great. Now there's no applet here to show what this graph looks like, but I know it's going to be some kind of curve because of the squareds and the square root. And what I really want to know is where is the derivative of this cost equal to 0? And that X value is probably going to be my answer, although there are ways that we can check it. All right, so let's go ahead and skip over to our calculator, and I'm going to move my calculator over here so you can still see all this. And so, oops, turn it on. And so I'm going to clear that. I'm going to do F1. I'm going to clear the home, and I'm going to clear my variables. If you don't want to clear your variables, that's fine. Just make sure you're using a variable that doesn't have anything stored into it. So first I'm going to differentiate. Okay, so F3, differentiate this 2 square root of 4,000 squared plus X squared. All right, plus, and you could do 1 or you could not, but I just want to make sure that you're able to do future problems like this. Okay, so that's the cost. Remember, we got to do comma X at the end since we're differentiating, and it'll tell you if you typed it in wrong. All right, so we get this weird thing, and I'm actually not even going to write it down. All right, I'm going to clear this. I want to know, by the way, if you get a number here and not something in terms of X, that's because you have a number stored in for X. Clear your variables, you won't have that problem. Or if you don't want to clear your variables, use another letter besides X. All right, so I want to solve for when this is equal to 0. We already said Y, so we're going to solve this. I'm going to go up here, grab that. This is very similar to what I did on the box problem. Equals 0. All right, and then comma, X, close parentheses, enter. All right, now I'm going to again get an exact answer. That doesn't really make sense here, so I'm going to do diamond enter. All right, now I get 2,309.401. Let's think about, does that make sense? Like in my applet, let me go back to the applet. It was somewhere between 2 and 3, but this was kilometers. So this is saying 2,000 meters. That does make sense. All right, let me bring that up, back up, so we can write it down. 2309.401. Let's see if I can remember that. And this is in meters. All right, if any of you, by the way, were getting confused about this, remember that this is not at 5. This is moving that way, it's moving that way. This is dynamic, this is changing. That's why we put X here. If this was actually at 5, I wouldn't have had to do all that work to find X. X would have been 5, but that's not what's minimizing the cost. All right, if I want to find the actual minimal cost, I need to go back to my calculator. I'm going to clear that. I'm going to take this, okay, and again, I really wish there might be an easier way to do this, but I need to store this in for X. Use those cut paste things on your calculator. And I'm going to go back up. I'm going to pull up where I did differentiating, but I'm going to take the differentiating part out. Okay, so I don't need that comma X at the end, and I don't need the DF. Whoops. It does not like it when I hold down that key. Okay, so I got to take out this DF because I don't want to do the derivative again. In fact, if you plug 2,309 back into the derivative, you're always going to get 0. All right, I want to plug it back into the original. In other words, I want to find C of this 2309.401, but I want to do it without the rounding. Okay, so really we should still be doing this because my answer is still not completely accurate. All right, and I get $16,928. This is a time when it's okay not to round to 3 decimals because you're talking about money. So we're going to do 16,928 and 20 cents. And put a little $sign right at the front. And so these two things combined are my answer. And you could write it out different ways, but that's what you get. Okay. Let's move on to another problem. And the second one we did was rowing and running. And if you're like, I don't have this paper, it's okay. Just write it on notebook paper. You don't need this copy. There's not much on there. Everything you really need is on these applets. So again, go to my Edline site, click on the rowing and running one. I already have it pulled up right here. This one's very similar, although it's a little bit harder, but the hard part is all just algebra, all right? So we have this thing where Maya's 2 kilometers offshore, so this is 2 kilometers right here, and she's going to row part of the way, all right, and then she's going to run the rest of the way. And this whole thing is 6 kilometers, and we have this nice little picture here. She can row 2 kilometers per hour and run 5 kilometers per hour. And what we're trying to do here is minimize the time. So it looks like the same picture, but it's a little bit different. Okay, so if I hit this plus, or this play right here, there we go. It'll show Maya rowing, and it'll give you her whole time and everything, and we could go through, and I would encourage you to go through this and figure out different ways to do this, and it'll keep playing it, and it'll show you all the different things that we could do. All right, and experimentally, it's going to take longer to find the minimum amount of time. If I click this optimal traveler, we can see that red is the best possible way because she's rowing a certain amount of distance so that even though she rows slow and she was running faster, she can have a longer distance running. Anyway, so this is what it takes. So I'm going to draw this picture. Let me pause this. Well, it did not want to pause. Oh well. Okay, there we go. So what we were going to do, and you need to get into the habit of drawing these pictures anyway, is we have this same picture that looks like this. Okay, and in the picture, this is where she's rowing, and this is where she's running. All right, this is a right angle. This is still going to be X. And since my speeds were in kilometers per hour, it's totally going to be fine if I stay in kilometers. This was 6 and this was 2. All right, so what I need to do is I need to come up with my rowing distance and my running distance based off of X. Again, this is going to be my 2 squared plus X squared. Square root around it because 2 squared plus S squared equals my road distance squared. So if I just want my road distance, I got to square root it. Do not simplify this. All right, and then the run is a little bit easier. It's going to be the total 6 minus this little piece cut out, which is X. All right, now let's think about how we write time. Okay, first of all, most of you know this. Distance equals rate or speed times time. All right, so what does time equal? It equals the distance divided by the rate. Remember here, rate, if you prefer, you could write speed. All right, so time equals distance divided by speed. All right, so we've actually got two different times to consider. We've got the time it takes to row, and we've got to add that to the time it takes to run, because they're different. All right, they're different distances, they're different speeds. So here's our expression. T of x equals, okay, my row distance is this square root, 2 squared plus x squared, divided by my row speed, which was, I forgot, so we're going to have to go back. Is that she can row at 2 kilometers per hour and she's running at 5 kilometers per hour. Okay, so my run distance is 6 minus x, and that's 5. Now, one thing I would encourage you to make sure you do here is that when you type this in your calculator, that the whole numerator is in one thing. Now, this is not going to be tough with the square root because you're already going to have it compacted like this. I'm going to go ahead and write 6 minus x in parentheses, because if you don't, you're not going to divide the whole thing by 5, which is what you want to do. All right, so again, what we're going to do in the calculator is to type that in, then we're going to find the derivative, we're going to set the derivative equal to 0, and we're going to get our x value. All right, and so let's do that. Okay, I already have something stored in for x, so I'm going to clear that out. And I am going to go ahead and clear the home screen as well, so it'll be easy to find things. So I'm going to differentiate in the square root of 2 squared. Now, if you wanted to write that as 4, you could. That would be fine, but no other simplification can take place. All right, so when you close the parentheses, that ends the square root, so we can divide by 2. You don't need another nested parentheses there. Okay, but if you had them, it would be okay. All right, plus, this is where you have to have parentheses. If you don't, what would end up happening is you would only divide the x by 5 and not the whole thing by 5. Remember, when you're differentiating, you got to do comma x. Okay, so we press enter, and we get this weird expression, and you can write that down, and that's fine, but really what I want to do is solve this equal to 0. So I'm going to do the F2, I'm going to solve, I'm going to go up and grab this, I'm going to set it equal to 0, comma x, close parenthesis, and I'm going to get a value. And I'm going to do diamond enter because it makes more sense to have an approximate answer here. So in this case, I hate that that goes away, 0.873, 0.873. Remember, this is in kilometers, so it's a little under a kilometer. And if I were to go back to this, it makes sense that the optimal traveler, which they kind of were nice and they gave to you, is a little under a kilometer. All right. Now, I didn't do this on the last one, and typically if you skip over this, you're going to be fine, but this could be a max or a min. Because we did the applets, we know that this is going to be the min. But to really be sure here, what you would always do is like how I did on the box problem. You'd put your number here, we'd have our derivative of t down there, t up there, and you'd plug in a number into the derivative that's less than your critical number, and this would be a negative. Okay, I'm going to spare you because it's hard to do this in your head. And then over here you plug in a larger number and you would get positive. Okay, it would not be into the, sorry, I pointed up here, we didn't write t prime. Remember, you're plugging these into t prime, and so that would cause t to decrease and cause t to increase after. That's for sure a min. So that's how you would do that part. All right, we need to plug this back in to actually find the minimal time. Maybe they don't want the minimal time. Maybe they just want this x value. All right, but if they want the minimal time, then what you need to do is go back to the calculator. And if you didn't want to do this whole store for x thing, let me show you just a slightly different way to do that. Okay, let me bring this down. Well, you know what? Never mind. I'm not going to do that. I'm just going to do the way I've been doing it. Take out that x equals, and then we're going to do the store x on this side. So store for x, and you could use another letter. Now I'm going to go back up to the differentiate. I'm going to select that, although I don't want to differentiate this thing. I really just want it. I'm going to take that out. And to me, this is the most efficient way of doing this. So this would be 2.117. And what are my units here? If my speed was in kilometers per hour, my time has to be in hours. And so that's going to be my minimum time, 2.117 hours. And if we wanted to go back to that applet, then we would get that. So that's not... Oh, we paused it. That's why they're not quite done. Let me press play again. All right, I already let it kind of go just a little bit, but 2.117. There we go. Okay, that's the end of that video. Please come see me if you have questions.